Hello everyone, I'm Qixing Wang from the Hong Kong Polytechnic University, the Department of Computing. Today I'm going to present our work on guaranteeing proper temporal embedding safety rules in wireless CPS, a hybrid formal modeling approach. First, we will spend 1 minute to give you the overview of our work, the rough idea of what this paper does. And then we'll dive into the details, the demand, problem solution, evaluation, and related work. Okay, so first, the overview. The main purpose of this paper is to reconcile a conflict. The conflict between the demand that life mission critical cyber-physical systems want wireless and the fact that wireless is by their nature unreliable. Of course, to fully reconcile this conflict is too huge a task for a single paper. Therefore, in this paper, we only focus on one subcategory of the problem: how to guarantee proper temporal embedding safety rules. Okay. And the approach that we take is by proposing a leasing-based design pattern. And we use hybrid modeling to formally describe, analyze, and implement this design pattern to achieve the PTE safety guarantee. Okay, so now let's get into the details. We know that cyber-physical systems, or CPS, are those systems involving complex and tight coupling of computers and other physical subsystems. Typical examples of CPS include avionics, robotics, and medical CPS. And CPS cyber-physical systems have all kinds of features. Here we list 3 major features that greatly shape the research of this paper. The first feature is that CPS are typically distributed and life mission critical systems. The second feature is that cyber-physical systems, in cyber-physical systems, real time in addition to logical time matters. For example, in medical CPS, suppose we're using a ventilator to supply oxygen to a patient in the surgery. Then if you pause the ventilator for 1 minute, then the patient might still be okay. But if you pause the ventilator for 1 hour, then the patient is definitely going to be suffocated to death. Therefore, real time matters. The third feature is that the formal modeling of cyber-physical systems must integrate both discrete and continuous aspects. Now let's see how these 3 major features shapes the research of this paper. First, because cyber-physical systems are typically distributed, we have the following demand. Distributed life mission critical cyber-physical systems demand wireless communications. Here is an example to illustrate why. This picture is describes a typical nowadays operation room. We see that in nowadays operation room, there are already lots of wires. It's quite messy. Actually, this is a hazard because people can trip over wires and cause accidents. Therefore, in medical CPS, people are talking about interconnecting the smart medical devices using wireless connections in order to reduce the use of wires to reduce hazard of tripping over wires. Same thing applies to other CPS systems, like control CPS. The less the wire that we use, the more the movement freedom. In avionics, for example, the drone swarm, we have to use wireless to control the helicopters. But here is the conflict. Wireless is by its nature unreliable. How are we going to reconcile this conflict between the demand that we want to use wireless in life mission critical CPS and the fact that wireless is unreliable? In this paper, we focus on the sub-problem of proper temporal embedding PTE safety guarantee. So what is proper temporal embedding, or PTE safety rules? I'll use an example and you will immediately understand it. This example is about laser tracheotomy surgery medical CPS. In the laser tracheotomy surgery, the surgeon uses a laser scalpel to cut open the trachea of the patient. On the other hand, the patient is under anesthesia. Therefore, we have to use a ventilator to provide the oxygen to the patient. And you can imagine if the ventilator is ventilating oxygen through the trachea and you shoot the laser, then the laser will trigger fire, causing accidents. Therefore, in laser tracheotomy, the interval that the laser scalpel shoots laser must be properly embedded by the time interval that the ventilator pauses. Okay. But that's not all. Remember the second feature of CPS, real time in addition to logical time matters. The time interval, they have real time requirements. The time interval that the ventilator pauses must be upper bounded. In a more abstract way, we say that the risky state dwelling time must be upper bounded. For example, the ventilator cannot pause for too long, for over 1 hour, then the patient must die. And then we have this enter risky safeguard interval requirement and exit risky safeguard interval requirement. In the ventilator laser scalpel example, it's like this. After the ventilator has been paused, the laser scalpel cannot immediately shoot laser because this can still trigger fire because there are still a lot of oxygen in the trachea. You must at least wait for T1 seconds before you can shoot laser. Okay. So this T1 seconds minimum requirement is called the enter risky safeguard interval. Same thing applies to the situation when you're stopping the laser emission. When you stopped shooting the laser, you must also wait for at least T2 seconds before you can resume the ventilation of oxygen. So these are the real-time requirements of PTE safety rules. Okay. So now, after understanding what is PTE safety rule, the question is how to guarantee PTE safety rules despite of arbitrary wireless link failures. When we think about this, we come up with the heuristic of using leasing design philosophy, using leasing design pattern. Leasing is a design philosophy proposed in 1989, first proposed for addressing for the research on distributed file systems. The main idea is that for any resource that you want to use, you must sign a contract, a lease, with the resource, specifying when the lease is going to happen and when the lease is going to end. When the lease expires, the resource will release itself automatically. So the leasing design philosophy introduces the concept of self-healing into the system. So inspired by this heuristics, we propose our leasing design pattern. In our leasing design pattern, we differentiate 3 kinds of roles. Each CPS entity must take one of the 3 roles. Initiator, the role of supervisor, or the role of participant. We can use an analogy to explain these roles and the interaction between these roles. The analogy is about throwing up a show, throwing up a singing show. Okay. So the singer who wants to put up the show should act as the initiator. She will request to the show manager, the supervisor. And then once the supervisor receives the request, the show manager should sign leases with the venue. Say from 8 a.m. to 8 p.m. the venue is leased. And then should sign another contract, another lease with the electricity. Say from 10 a.m. to 6 p.m. The electricity is leased. Then, with all these resources leased, the supervisor, the show manager, can approve the request to put up the singing show. Okay. And then we will have the show. This is the time interval that the venue is available, which should properly embed the time interval that the electricity is available, and which in turn should properly embed the time interval that the show is put up. Also, so this is the main idea of our leasing design pattern. Also, our design pattern must take care of the real-time requirements. we need to take care of this upper bound requirements, these enter risky, exit risky time interval requirements. We also need to think about the aborting and canceling situations. The singer can cancel, the initiator can cancel the performance, the show manager can abort the performance, and also the communication links can fail arbitrarily. So this is the things that we need to consider in addition to the main idea of the leasing design pattern. All right, with these concepts in mind, the next thing that we need to take care is how to formally describe, analyze, and use the leasing design pattern in the context of CPS. Here is where the third feature of CPS comes into play. The third feature says any formal modeling tool for CPS must integrate both the discrete and continuous aspects. So this feature inspires us to use hybrid automata as the formal modeling tool. Hybrid automaton is a state-of-the-art modeling tool for CPS. Here's a short example to illustrate what it is. The example is about bouncing ball. Suppose I have a ball in hand, I let it fall, the ball will free fall, hit the ground, and bounce back. This kind of behavior can be described by a hybrid automaton, like this. The main difference is that compared to the conventional automaton is that the node is no longer a discrete label. Inside the node, there is a set of differential equations describing the continuous behavior of the system. Here, x1 represents the current height of the ball. So the derivative of x1 is the velocity of the ball, x2. The derivative of velocity, x2, is the acceleration, which is the gravitational acceleration of the ball. Okay. So when the ball is in air, its continuous behavior is governed by this differential equation set. Once the ball hits the ground, a discrete event takes place. In this discrete event, the velocity of the ball will change direction, and there will be an energy loss. Once the discrete event takes place, the ball is in the air, and the differential equation takes charge again. So using hybrid automaton, we can easily describe both the continuous and the discrete behavior of a system, the cyber-physical system. So inspired by this, we designed the hybrid automaton for, we designed the hybrid automaton for the supervisor role. We designed the hybrid automaton for initiator and hybrid automaton for the participant. So using hybrid automaton, we can describe our design pattern. The detailed design of these hybrid automaton are available in the paper, which I'm not going to elaborate. The thing that I want to bring to your attention is that in all these hybrid automaton, we have various temporal configuration parameters. And it is these parameters that plays a role to guarantee the real-time properties of PTE safety rules. We have the following theorem. If the temporal parameters of the design pattern hybrid automata satisfy a certain set of linear inequalities, then PTE safety is guaranteed despite of arbitrary communications link failures. So this slide shows you this set of constraints, linear inequality constraints. The details of these constraints can be found in paper. What this slide wants to communicate are two things. First, this set of constraints is non-trivial. Second, this set of constraints are linear. Therefore, you can still use all kinds of well-known linear optimization software packages to apply to this set of constraints to derive the optimal configurations for your detailed design. All right, so now we have the formal description of our design pattern. The next thing that we need to do to address, next problem that we need to address is how to use these design patterns. specifically how to turn the design pattern hybrid automata into the detailed CPS designs. To do this, we proposed a formal procedure to elaborate a design pattern hybrid automaton into a detailed design hybrid automaton. For example, if this hybrid automaton describes our design pattern, then through our elaboration procedure, we can add more details into, for example, the fallback node. This is after elaboration. The fallback node expands into a component hybrid automaton. We add more nodes into it, and we can add more parameters into it to turn the original design pattern into a more complex, more detailed CPS design. We further prove that if the detailed design hybrid automata are respectively derived by elaborating corresponding design pattern hybrid automata, then the PTE safety is guaranteed despite of arbitrary communication failures. Okay. So now we have the specification of our design pattern. We have analyzed its property, and we know how to use these design patterns to derive detailed designs. Now, next we use a case study to evaluate our proposal. This case study is about laser tracheotomy medical CPS. This picture is taken from a conventional laser tracheotomy surgery. One typical kind of accident in conventional laser tracheotomy surgery is that the surgeon mistakenly shoot laser scalpel from the laser scalpel when the ventilator is still on, when the ventilator is still ventilating oxygen into the trachea of the patient. Then the laser will lit fire. Okay. To avoid this kind of disastrous accidents, laser tracheotomy medical CPS proposes to interconnect and interlock smart medical devices to increase safety. Specifically, the laser scalpel and the ventilator should be interconnected. If you want to shoot laser, the ventilator must be paused. If the ventilator is working, you must not allow the laser scalpel to shoot laser. Furthermore, people want to use wireless links in the laser tracheotomy CPS. The reason is because nowadays operation room is too messy. There are too many wires, and if you add even more wires for interlocking, then this will literally turn the operation room into a spider web, and people can easily trip over wires and cause accidents. If you have wireless, then we can reduce the amount of wires to reduce the hazard of tripping over wires. So this literally turns the laser tracheotomy CPS into a wireless CPS scenario. Furthermore, in laser tracheotomy CPS, we need PTE safety. Specifically, the interval that we shoot laser must be properly embedded by the interval that the ventilator pauses. That's not all. The ventilator pausing interval must be upper bounded. We cannot pause the ventilator for over 60 seconds. Otherwise, the patient might be suffocated to death. Also, after you have paused the ventilator, we cannot immediately shoot laser. We must wait for a minimal time interval, 3 seconds, before we can shoot laser. Same thing, after we have stopped shooting laser, we must wait for at least 1.5 seconds before we can resume the ventilation of oxygen. So this means that we can apply our aforementioned leasing design pattern to enforce the PTE safety rule, to guarantee the PTE safety rule in the wireless CPS of laser tracheotomy. The specific designs like following. We designate the laser scalpel to take the role of initiator, and the supervisor will take the role of supervisor, and the ventilator and the patient together will take the role of the participant. And according to the methodology that we have described before, we can come up with the detailed design hybrid automata for laser scalpel, for the supervisor, and for the ventilator. And then we can evaluate. Of course, as a computer science advisor, I cannot really carry out surgery on my PhD students. So what we do is emulation. We use 3 laptops to respectively emulate ventilator, supervisor, and laser scalpel. The ventilator emulation laptop will show on its screen pumping out, pausing, pumping in. When it shows pumping out, the PhD student here will inhale. When it pauses, then the PhD student here will hold his breath. When it pumps in, then the PhD student will exhale. And the blood oxygen level of the student will be measured. It's measured in real time by the supervisor laptop. Now, laser scalpel laptop only show on its screen, I'm shooting laser, I'm stopping laser. But these behaviors are logged in real time. All these 3 laptops communicate with each other using Zigbee wireless links implemented by T-Mode SkyModes. And then 2 meters away, we put a wireless interference source implemented by an IEEE 802.11g access point. This access point will continuously send out data, Wi-Fi data. And the only purpose is to jam the Zigbee communication links here. And this is our emulation results. We carry out 4 trials, and each trial lasts for 30 minutes. In trial 1 and 3, the design is, we follow the leasing design pattern. And in trial 2 and 4, we do not deploy the leasing design pattern, which means the ventilator has to be explicitly turned on and turned off by the supervisor. If the communication link fails, the ventilator will stuck there. So in the first trial, we can see that the laser scalpel requests 19 times for emitting laser, for shooting laser. And there is 0 violation of the PTE safety rule. In trial number 2, you see that the laser scalpel requests to shoot laser for 11 times. And there are 4 violations of the PTE safety rules because of the failure of wireless communication. The same situation applies to trial 3 and trial 4. If we have lease, there is no violation. If we don't have lease, there is violation. Okay. Related work. Leasing is a design philosophy proposed in 1989 by Gary et al. So there are lots of protocols and designs based on leasing design philosophy in the literature. However, they are all these existing works. They are for purely cyber systems and computer systems. Compared to these works, our work is different because of these 3 context change. The first one is that for purely cyber systems, the computer systems, people can do checkpointing and can do rollback. But for CPS systems, we cannot do that. For example, we cannot kill a patient and then roll back. It's impossible. The second context change is that in the purely cyber systems, people care about logical time. But in CPS systems, we care about both logical time and real time, Proper-Temporal-Embedding. Those upper bounds and lower bounds of time intervals does matter. And then the third context change is that in the purely cyber systems, everything is a computer variable under the control of computers. But in cyber physical systems, lots of things are physical world parameters that is not fully controllable by the computer.